Okay guys, welcome back. So last time we defined and discovered this new class of problems, this new complexity class. What was that? Well, that was the NP-complete problems. What are the NP-complete problems? Well, they're the hardest problems to solve in NP. So we found out, and I told you that there's more than one of these problems. It's kind of like a tier of difficulty of problems, but they're the hardest problems to solve in NP. Okay, well, how did we show a language or a problem is in NP-complete or is an NP-complete problem? Well, you essentially had to do two things. The first thing is you have to show it's in NP. I mean, in order for it to be an NP-complete, it's a subset of NP, therefore it has to be an NP problem. So you have to show that you can verify it in polynomial time. Okay, fair enough. And the second thing is you need to be able to show that all other NP problems reduce to that problem. So that means if I solve the NP-complete problem, I get a free polynomial time solution for all the NP problems for free. Okay, well that was all well and good, but remember, that only works when you have an NP-complete problem to start with. And, it's a little tricky without it. Well, lucky for us, we saw a theorem last time called Cook's theorem, and what that stated was this 3-sat problem. If you forget what that 3-sat problem is, go check out the last part. That 3-sat problem is NP complete. Okay, so 3-sats NP complete, that's going to be, our building block, our initial building block, our foundation. And we're going to show that from this 3-sat, we can reduce 3-sat to, independent sum, or independent set, independent set to other things, maybe the subset sum to knapsack, to traveling salesman, and we just go down the line essentially and prove all these problems to be NP complete. Okay, so that's what today's going to be all about. We want to come up with as many more NP-complete problems as we can because, given a new problem, if it is NP-complete, technically 3-sat's going to reduce to it, but it might not be as intuitive as another problem. So we want to build up a big toolbox of NP-C problems, NP-complete problems. So when we want to determine something else is NP-complete, we'll say, okay, it's kind of like this problem. Let's start with that one and see if that one reduces to it. So we want to come up with as many candidates as we can for these NP-complete problems. So, in that spirit, let's start off with building that toolbox, and let's try to show, and I'm going to do it on this board, prove the independent set problem. If you forget what the independent set problem is, go back to last lecture where we looked at independent set, vertex cover, and the click problem. Prove independent set is NP complete. Okay, well, how are we going to show that the independent set problem is NP complete? Well, we first have to show that independent set is in NP. Is independent set in NP? Yes, it is. We had talked about that before, but you can certainly verify a potential solution to the independent set problem in polynomial time. You just loop through all the vertices. Is this one connected to any of the other ones in this potential independent set? If it isn't an independent set. And then you get through them all and none of them are connected, it is an independent set. Okay, fair enough. It's in NP. Now we have to show that another NP complete problem reduces to it. Well, we only have one problem right now. So the way that we're going to do this is show that 3-sat reduces to independent set. So what that means is, given a general 3-sat problem, if we have access to an independent set black box, we can solve the 3-sat problem. It does not mean, this is one of the most common fundamental mistakes students make, we do not have to be given a general or an arbitrary instance of the independent set problem and solve it using a 3-sat black box. Not the case. We just have to have a general instance over here and be able to solve the general instance of 3-sat using independent set, not vice versa. Okay. Well, you could call this a proof. It's going to be a little bit hand-wavy. The devil's in the details, but hopefully you guys are going to see, how I can use the independent set problem to solve the 3-sat problem. And it is one of those proofs where it is kind of just easier to show you guys how I'm going to construct, because you look over here, this is a logic problem. This is a Boolean expression. Independent set, is it a Boolean expression? Not at all. It's a graphing problem. So how are we going to relate a Boolean expression to a graph? Well, it's one of the things where it's just going to be a little bit easier to show you guys. So remember, for the 3-stat problem, I want to determine, is there an instantiation of these Boolean variables such that this entire expression evaluates to true? Now for this particular problem instance, I mean, there's only 3 terms here, so even the human mind can look at it and be like, obviously there is. But I'm going to show you how you would use the independent set problem or a solution to the independent set problem to give you a solution to this one. So the general idea is this. For each term, I'm going to create a graph that has like a triangle corresponding to each term. And when I say a triangle, I mean like a 3-click. So 3 nodes that are all connected to each other. I'm going to connect all these things together. So this one in some way is going to correspond to this term. So this one in some way is going to correspond to x1 or not x2 or x3. And I'm just going to create one of these 3-clicks or these triangles for each term. And I'll put a labeling on these nodes. So 1, 2, 3, 4, 5, 6, and 7, 8, 9. Now here's the idea. Each one of these nodes is going to correspond to one of the Boolean variables up here in the term that this triangle is corresponding to. So for instance, maybe this node 1 here, that's going to correspond to the Boolean variable x1. This 2, that might be not x2. x3, that's going to be x3. So that one's intuitive. This one, maybe the 4 is going to correspond to not x1 here. This one's going to correspond to x4. This one's going to correspond to not x3. This one up here is going to correspond to x1. This one over here is going to correspond to x2. This one over here is going to correspond to not x4. Now here's the idea. I'm looking to see if this thing evaluates to true. Well, the way I'm going to do that is, assuming I have a black box that solves the independent set problem, I'm going to give it this graph, and I'm not done creating this graph yet, but I'm going to give it, this graph after I do a few more things, a few more hookups, and ask, does there exist an independent set of size k, where k is the number of terms. So here, k is 3. This is the first term, second term, third term. K equals 3 here. So if I were to just throw this graph, remember this graph, it's not connected. It's not a connected graph, but it's still a graph. If I were to ask it, does there exist an independent set of size 3 in this particular graph? Does there? Well, yeah, of course there does. For instance, I could choose 1, 4, and 7. Now those nodes are connected. So that's an independent set. So is, 2, 4, and 9. There's many independent sets of size 3, but there's certainly at least one. Okay, is there an independent set of size 4 in this graph? No. Because as soon as I choose one node from each of the triangles, I can't choose anything else. I can't have 2 nodes from a single triangle. Therefore, 3 is the max here. And the idea is, I want, for instance, if it returned me the independent set 1, 4, 7, that should correspond in some way to a valid instance of these Boolean variables up here that evaluate this to true. But here's the problem. If, for instance, it returned 1, 4, and let's keep it a little more general here. So let's say 1, 4, and 8. So if I were to inspect the independent set of 1, 4, and 8, the corresponding solution to this would be, okay, set the Boolean variable x1 to true. Set the Boolean variable not x1 to true. And set the Boolean variable, what's 8 down here, x2 to true. Well, I can set x2 to true, that's fine, but I can't set x1 and x1 bar to true at the same time. That's just not the way it works. Review your Boolean expressions there, true can equal false. So this independent set would not correspond to a valid instantiation of these Boolean variables up top. Well, how am I going to address that? I guess I can leave that up for now. I want my independent set solution, my black box here, to not be able to choose 1 and 4 at the same time. So an independent set cannot have 1 and 4 in that set at the same time. Well, how do I prevent independent set from considering that solution? Well, I mean, it's an independent set if these things aren't connected, but if they are connected, it's no longer an independent set. So if I want to stop this independent set solution from considering that particular solution, I hook up those two nodes. Now, the independent set problem says, okay, well, I can't choose 1 and 4 at the same time. So maybe it does something like, okay, I'll choose 1, 5, and 9. So maybe my second choice is 1, 5, 9. Does that correspond to, a valid independent set in this graph? Yes, it does. I take 1 and 5 aren't connected, 9 isn't connected to 5, isn't connected to 1, so we're all good to go. So what does that correspond to up here? Well, it says, okay, set x1 to true. Okay, cool. So that's going to make this term evaluate to true. 5, set x4 to true. Okay, so that's going to make this term evaluate to true. So now we just have to make sure this one evaluates to true. So we said 9. Well, that's not x4. Well, hold up. Same problem as before. I can't have x4 and not x4 be true at the same time. So I need to connect these as well, because that's not a valid solution. And the idea, and you're probably already ahead of me here, is I'm going to look at every Boolean variable. Does its negation or the representation of its negation exist somewhere in this graph? If so, connect it up. Okay, so let's just get rid of those. And it's likely that I'm going to make a mistake here. I'll do my best. Okay, so there's a not x2 here, x2 over here. I have to make sure that, okay, 2 and 8 aren't selected at the same time. So I'll connect those two. What else do we have? Well, look, we have not x1, we have not x1 over here. Have to connect those two. X3, not x3. And now you start to see this graph begins to encode kind of the relationship that these Boolean variables have up here, and it's constraining it, right? In the same way that the resat is kind of constraining each of these terms, now we're constraining each of these little triangles here. So we're constraining more and more independent sets, and we are hopefully doing it in such a way that if there's a solution here, there's going to be an independent set down here, and vice versa. If there isn't a solution here, there isn't going to be an independent set down here of size k. Okay, any other connections that I missed? Maybe. You can check if there is, corrected, of course, in your notes, but I think I'm in solid shape. So, does there exist an independent set of size 3 in this graph? So now I've done all the hookups for this graph. I'm going to ask my black box, does there exist an independent set of size 3? Well, let's try. Let's try to build one. I'm going to take 1 to start out with. Okay, well, 1's not going to let me take 4 over here. That still leaves the choices of 5 and 6. So I'll take 5. Why not? 1 and 5. Okay. Over here, can I take 7? Because look here, I took 1 over here, and it's kind of connected to this one, it's connected to this one. Doesn't matter though. Why? Because this one, node 1 over here, is not connected to the node 7. So I can still take the node 7, for instance. And it says, yes, there is an independent set of size 3. Here it is. And that's going to correspond to the solution. Well, look, just set x1 to equal true and set x4 to equal true. That's 1 and 5 here. And this is redundant, actually. This is saying, okay, also set x1 to equal true. But basically, this is saying set x1 to true, set x4 to true, and that's going to satisfy this Boolean expression. Does it? Yes, because this one evaluates to true because we have true or some stuff. x4 is in this one, so we have true, and x1 is in here again, so we also have true. Okay, good. Does there exist another independent set of size 3? Yeah, it probably does. There probably exists many of them. And again, it's hard to show you with a small example here with, for instance, just 3 terms when there isn't actually a solution. But I'm going to leave it as an exercise for you guys to convince yourselves. Again, it's a little bit of a hand-wavy proof here, but I want you guys to convince yourself, yes, I see how this graph exactly corresponds to this Boolean expression. I see how this is going to have an instance that value is to true if and only if in this graph down here there exists an independent set of size k. So again, it's not like the most formal proof in the world, but it is pretty convincing, and you should be able to kind of connect the dots here, or connect the nodes, figure out exactly why it's the case, and try to come up with like maybe a trivial example to show yourselves when there isn't an instantiation of the Boolean variables. In fact, take this one for instance, x1 or x1 or x1 and not x1 or not x1 or not x1. So draw that into an independent set. Ask it, does there exist an independent set of size 2? If you do it correctly, there does not. The largest independent set, if you have all the hookups correct, is going to be size 1. Okay, so what does that mean? That means independent set is NPC, is NP complete. Well, that immediately implies 2 other things are NP complete. What's that? Well, that implies vertex cover and click are also NP complete. Why does that imply that? Well, remember from last lecture, not the last part of this lecture, but in lecture 10, we showed that vertex cover, click, and independent set all reduce to each other. Well, if independent set is NP complete, that means it reduces to vertex cover and click, and vertex cover and click also from last lecture, from lecture 10, are also an NP, therefore they're also NP complete. Okay, so with this reduction, we've got 3 new NP complete problems. So whenever we want to try to show that a new problem is NP complete, we have these 3 problems available to us, as well as 3 set to work with from the ground up. Okay, cool. So that's our first little add-on here, 3 new problems. I'm going to give you another problem. Subset sum. What is subset sum? Well, given a set of integers, call it S, set of integers S, and a target number T, and a target T is also just an integer. Does there exist a subset of S that sums exactly to T? Does there exist a subset of S that sums exactly to T? Is this a hard problem to solve? Well, what if we were to brute force it? So given S, maybe it's size n, so we have n numbers to work with. And we want to know, does there exist a subset in there such that all the numbers in that subset sum exactly to T? Well, how many subsets are there? Well, again, typical stuff, and this should be very intuitive to you at this point. If I have a set of size n, the number of subsets is 2 to the n. I have to sum each of these subsets up. Well, brute force, again, is going to be at least exponential. Okay. So brute force is hard. Does there exist a clever algorithm that solves it better than that? Maybe. Maybe there is. But again, very similar pattern to all these other problems we looked at. I'm not saying there doesn't exist a better solution or a clever solution that solves this in better time than exponential, maybe something like n cubed or n to the fourth or something like that. But I don't know about it. And when I say I don't know about it, I mean the general computer science community doesn't know if that algorithm exists or not. So this is really the best we have, and what I'm getting at here, again, you should see a pattern with these problems. Okay, well, I can't solve this thing in polynomial time. I should say I don't know how to solve this thing in polynomial time if I can. However, can I verify a solution in polynomial time? Think about that. Yeah. Well, what would a solution look like, a potential solution look like? Well, it's going to be a set of numbers. What's the first thing I'd have to check about that set of numbers? Does it sum to t? If it does, I also have to check, does each one of those numbers actually appear in S? If it does, then it's a valid subset, and it sums to t, so that solution is correct. If not, then it's not a valid solution. Okay, so this thing is in NP. So subset sum is in NP. Is it NP complete? Well, what do you think? I mean, if it wasn't NP complete, it'd be kind of weird for me to be bringing up this problem right now, specifically in this lecture. And it turns out, yes, subset sum is NP complete. However, I'm not going to show you the proof of that here. It's in the textbook. It gets to like low-level stuff that it's just not really fun for me to do. Maybe it's fun for you. I mean, whatever floats your boat. But like, if you're interested in this proof, go check out the textbook. But we're going to move forward, assuming that we know, and we do know, that subset sum is NP complete. Okay? Check the textbook for the proof of that. All right, so that's another problem we have. And we can use that to prove new problems that are NP complete. It's another tool in our toolbox, another building block you can think in our NP complete problem set. I'm going to hit you up with another problem. Partition. The partition problem. What's that? Well, given a set of integers s, and that should already ring some bells, like a set of integers seems similar to the subset sum. It is. So given a set of integers s, does there exist a P1 and P2 such that the union equals S, the intersection equals S, or sorry, the intersection equals the empty set, and here's the important part. So those two things hold, and the sum of all the numbers in P1 equals the sum of all the numbers in P2. So I mean, that's the mathematical definition. This is actually a very intuitive problem if you're getting a little bit lost here. So given a set of integers, is there a way I can split those up into two, distinct parts such that they sum up to equal values? So is there a way to divide these sets of integers so they add up to the same thing? And I'm wondering, is that a hard problem to solve or not? Now, I'm always interested. I want you guys to ponder this. What's harder? Partition or subset sum? And you don't necessarily need to think of this in the framework that we've done it. Just in general, if you were given this problem, maybe in like first year programming, for instance, back in your 108 days, and you're asked to solve this, which one would be a harder one to solve? Now pause the video Just ponder that for a moment. 1, 2, 3, and we're back. So I find this actually interesting because the past 2 years I've always posed this question to students, and like not only with the majority, but a vast majority of the student body seems to have the intuition that partition is the harder problem. And again, I'm going off on a tangent here, and I've been trying to understand why that is. But my intuition when I first saw these two problems is subset sum is the harder problem. And I'll be honest, when I first saw it, I was actually shocked to learn how difficult partition actually was. So maybe someone can reach out to me and exactly, if you did have that same intuition as the majority of the class, that partition is the harder problem than subset sum, maybe you can explain that to me, because I just don't follow along with that. Let me show you why I have the intuition that subset sum is the harder problem to solve. So imagine I'm given a partition instance, an instance of the partition problem. So I want to know, is there a partition of S? Well, coming up with yes or no answers to that can be tricky. Is there a partition of S? That's a hard problem. But what if I had a subset sum black box? What if I had a subset sum black box where I could give it some set, maybe S prime, it might be S, but just in general it's a set of integers and a target, and it gives me for free a yes or no answer. Well, think about this. If I have access to this black box, this problem becomes very, very easy. Why does it become very, very easy? Well, think about this. If I want to know the answer to this problem, what do? Well, I first figure out what the sum of all these numbers is. So I sum up all the numbers in S, and I'm playing it pretty loose with this notation. When I do this, I mean I'm summing up all the numbers in that set. So I sum up all the numbers in that set, and let's say that equals lowercase s. Well, in order to determine if there's a partition, all I have to do is say, okay, well, if all the numbers in S sum up to lowercase s, does there exist a subset sum in S that sums up to lowercase s over 2? If there does exist a subset that sums up to s over 2, then there's a partition. Why? Well, I think this is S. If this sums up to s over 2, then this sums up to s over 2. So if there is a subset sum of s over 2, then there's a partition. And if there isn't a subset sum of s over 2, then there's no way I can make a partition. So asking the subset sum problem this solves the partition problem for me for free. And that's where my intuition behind this is. If I can solve the subset sum problem, partition is solved pretty easily. It's basically kind of like a sub-instance of the subset sum problem. It's an easy problem to solve if I have access to the subset sum black box. Well, okay. Well, if that's true, there's probably a reduction embedded in here, right? I've been saying like black box and stuff like that. Well, that means partition reduces, polynomial time reduces to subset sum. Oh, interesting. Does that prove anything though, really? Well, when I say prove anything, obviously it proves something. But really what I'm after is I want to come up with new NP complete problems so I can use it in reductions moving forward. Okay, well, partition reduces to subset sum, and subset sum is NP complete, then partition is NP complete? No. I need to show, if I want to show that partition is NP complete, well, first of all, I have to show it's in NP. It is. I'll leave that as an exercise for you. It's not hard. But it is in NP, but in order to show that partition is NP complete, well, if I'm using subset sum, I need to show it the other way. To show that partition is NP complete, I need to show that subset sum reduces to partition. That seems a lot trickier. Because remember, subset sum, now I have to deal with a general instance of subset sum, and the target sum could be way, way off of half of the sum of the entire set. That targets could be anywhere. And how am I going to use the fact that does the set have a partition or not? How's that going to in any way tell me if there's a subset that sums to a general T? That seems like it's not going to work out. But maybe it does. Maybe there's something clever we can do. And again, it'd kind of be a letdown if I brought this up and then told you, actually, you know what, I don't know why I brought this up at all, because partition isn't an NP complete problem. Partition is an NP complete problem, and there is something clever we can do to show this reduction. But I'm probably a little bit over time. We'll see this reduction in the next part. Okay, thanks for your attention.